The vector PQ has the initial point at P and terminal point at Q. So we're going to find that vector by subtracting 7 minus 2, comma, 2 minus 4. So that vector is 5, negative 2. Now, what that means is that that particular vector is this one. That's 5, 2. You can call that, so that's PQ at the same time. Now I can also draw the red one, which goes the other way, which is the vector QP. And the vector QP is going to be the other way around. It's going to be 2 minus 7, comma, 4 minus 2, which is negative 5, positive 2. So that vector is, yeah, I have no room to draw that vector, but it's going to go this way. I know I can move the page to fix it, but then when I export in PDF for your notes, it's going to be bad. So I'm not going to do that. But the vector QP, it's going to go that way. So these two vectors are not the same because they don't have the same angle. They have the same magnitude. And in terms of the angle, they're 180 degrees apart, which means they are completely opposite of each other. So this is that part where we can claim that PQ is equal to the negative QP. And you can see that it's a matter of multiplying, distributing negative 1 to actually make them the same. So these two vectors, not the same. So they have same magnitude, but they don't have the same direction. And we can actually write that the vector PQ is equal to negative QP. Make sure you have these arrows above letters, because that means it's a vector. That's the notation. So these are not the same vectors, even though they have the same magnitude. They don't have the same angle. All right. So now, what can we do with vectors? We can change the size of the vector without changing the angle of the vector by simply multiplying that vector through by a constant. We call that scalar multiplication. So if I have a vector u given as 3, 4, I can go and say 5u is going to be simply 5 times vector 3, 4, which is 15, 20. When you multiply a vector by a constant, you simply change its size, its magnitude, the angle remains the same. So scalar multiplication changes the magnitude direction stays the same. So we can change the size of the vector. I can also add or subtract vectors. So how do I add or subtract vectors? Well, we're going to add real to real, and then real to real. Wow, I was talking complex numbers. X components to X components, and Y components to Y components. That way they will add. So let's go and have vector U, let's say 3, 7, and vector V, -1, 4, whatever. So as I mentioned before, addition of these two vectors, so U plus V, is going to add 3 plus -1, comma 7 plus 4, which will give us 211. And let's go U minus V, which will be 3 minus -1, comma 7 minus 4, and this is 4, 3. So now what's happening here? Let's draw. Let's draw these. You have square paper? Great. 3D is going to be a living nightmare if you don't have it. First vector is 3, 7. It's vector U. And the second vector is -1, 4. That's vector V. So there are vectors U and V. Yeah, it's not going to fit here. You don't have to change your picture. It's just not going to fit. -1, 4. Three, 7. So vector U and the vector V. So how's the addition? Addition is we simply link two vectors together. I'm going to pick up, because vectors are free to move in space, I'm going to lift vector V and move its initial point to the terminal point of vector U. So I'm going to here go -1, 1, 2, 3, 4. This is vector V. And I'm going to have the resultant and if you look at the resultant, this point here is 211, which is exactly what the answer for the vector was, because vector stretches from origin all the way to the terminal point. So I have 211, and that was addition. I can do the same thing for subtraction, except for subtraction, I am going to add negative v, which means I'm going to go 1 unit to the right, 4 units down. So that's negative v. And then you have the resultant, which is now u minus v. And you can see clearly it's 4, 3, which is exactly what we had, 4, 3, earlier. So as long as you are adding and subtracting these vectors component-wise, you will get the right answer, right? So we start with vector u. We either add or subtract vector v, and we get the new vector, which is the sum of the two. So this vector over here is u plus v. We good? Awesome. Vector multiplication will be studied later. We call that dot product and the cross product. So we're going to skip that. The only two operations that we do now are scalar multiplication, and we're talking about adding and subtracting vectors. There is also something that is called a zero vector. Zero vector is the vector that has a zero magnitude, and it's technically the origin. That will act as 0. So let's take a look at these properties now. Now, textbook uses bold letters to represent vectors. Since we don't bother with bold letters, we actually put arrows above variables which represent vectors. So u plus v is the same as v plus u, commutative rule. Then we have associative rule. U plus v plus w is u plus v plus w. That's associative rule. V plus 0 vector is the same vector v. We have additive inverse. When you add v to the negative of v, you get 0 vector. Number 5, distributive property. We have 2 of those because the nature, we'll see. So distributive property, you get AU plus AV. 6. A plus CU is AU plus CV. No, CU. Zero times vector v is 0 vector. C times 0 is equal to 0 vector. One times vector v is vector v. And finally, A times CV is AC times V, another associative property. I can't show all 10 at once. I mean, I can, but I don't want to. Those of you interested in honors section, this would be one of the lists that you will work the proofs for. I am going to show a proof for one of these or two of these, so you guys can practice. All of these problems are pretty much done the same. What you need to make sure, guys, is that honors or not, that this 0 here is the number 0 that you guys know from your regular, right, numbers, and this is a 0 vector. So observe that you multiply 0 into a vector, you get a 0 vector. So vectors have two aspects to themselves. They have magnitude and direction. I'm just going to kill a sound. I'm not sure if it's coming from here. So let's work out any of these. Just which number? 7? Is that what you said? 7. Awesome. Since we are in 2D, proof for number 7. 0 times v is equal to 0 vector. So vector v, see you next week, is given as v1, v2. Those are the components, x and the y component of the vector. So 0 times vector v1, v2. We use the rule where 0 distributes inside to each of the components. So we have now 0 times v and 0 times v2, which is 0, 0, which is the 0 vector. All right. Let's do one more. Choose wisely. Which one? Oh, you have no idea. I'm going with 9. No, that's perfect. I mean, it's identical to what we did up there. So we defined vector v as v1, v2. So now I'm going to write. I was about to cut and paste. It's just important that you guys are happy, you know. You wanted to see number 9? There you go. Awesome. So there's a proof for number 9. Your honors exam will have like numbers 5 or 6 or something like that, but that's okay. You'll figure it out. So you write the vector as components, and then you just follow calculation through. Good. So applications of vectors. What can we do with these things? Well, vectors represent, as I said, many things. For instance, time is not a vector because time doesn't have, we don't think of time in terms of direction, right? Time flows forward and we're content with that for now, I guess. Mass is another thing, just magnitude, right? But then you have these things that will have direction and magnitude. For instance, force would be one of them, which is pounds. So when you go and buy 3 pounds of bananas, you don't actually pay for bananas. You're paying for, the force which pushes. Exactly. If you are to buy a kilogram of bananas, then you're paying for bananas because mass. Anyway, yeah, I know. Think about that. Get ripped off every time. So force is one of them. It's important which way we direct the force, and then how much of the force we are applying. So we're talking, right? So not much force, a lot of force. So that's adjusting the magnitude without, I hope there's no, actually even if there is, I don't care. They're awake now. Someone shows up at the door. You guys okay? Yeah. Leave. That's why I have this here. So applying the force, it's important in which direction you apply and how much. So that's one of the things. What else is a vector? Velocity, very good. So, speed limit 65 on 78, they're just banking on the common sense that you will not be going the wrong direction, right? Because speed is the magnitude of velocity. So technically, when you read speed limit 65, they're telling you magnitude is 65. You can go any direction you want, right? It's just so that we, want to preserve our lives that we are going with the flow. But technically, by law, you are free to go any way, I guess, because the sign doesn't say velocity limit 65 miles per hour due east, let's say, or due west, or something like that, which they should. So velocity. Also, acceleration is another one. You have those two in your car, right? The gas and brakes. Acceleration and deceleration, they both change velocity, positive or negative way. So again, it's a vector. How hard you apply the brakes how hard you push on the gas pedal is changing the magnitude, right? And then the direction is which pedal you actually press. So there is the application right there. Anything else? Momentum. Okay, momentum. Perfect. What else? What is the momentum? Yeah, but what does it do? Physics. Long time ago? Like last semester. I know. I was about to say last year. You just pushed the limit like last semester. I was about to go last class. Last week. Long time ago. What is momentum, guys? You can explain momentum. Yeah.
It's the vector that's velocity times mass.
We heard that already, but what is it? He said that.
I couldn't hear very well.
Okay, it's fine. What is it?
The force that keeps something going.
Oh, it's inertia.
All right, so here it is. Car slamming into a haystack, car slamming into the wall. Go figure it out. Yeah, it has both. All right, good. Torque. What's torque? Yeah, well, that's that now. I'm just making it worse. Yeah, it's circular force, yes. Okay, so you're thinking on the screwdriver, all right, you're applying the force in a circle, all right? But you can also think about opening the door, the hinge, and so on. Anyone taking statics anytime soon? I'm taking statics now. Oh, good. You're going to learn all of those things. That'll be awesome. Physics one have wonderful times with labs. Right? Yeah. Yes, a lot of students go, oh my God, your projects are insane. And then they come in and say, your projects were wonderful. Now we got to do one project a week in those labs. Good. What else? Do we have any other forces that we can think about? Gravity, but what kind of force is that? Actually? No. Yeah, but it's acceleration. Yes. Friction. Friction. Yes. Friction. So there's a lot of different concepts in physics that we explain by vectors. But also, I already talked about me being a vector. Here's another example of a vector, right here. It has its magnitude, right? If this was 3 miles long, I would not be able to use it, right? I would not be able to wield, well, actually I would, but you wouldn't. But look, if I use it the right way, it works. If I orient it this way, it doesn't work, and so on. So it's a vector. It does have magnitude. It has orientation because certain orientations work and certain orientations do not, right? So that would be, so it's not just physical concepts like force and velocity. It's also objects that we can represent by vectors. And you have a lot of different concepts that you can deal with. So that's that part. I'll get my art off of this so you guys are not distracted by it. Good.
Okay.
Yo.
When we're talking about like magnitude being length, where does that come into play with like the force and half length?
It does. That's the part of how hard you hit. That was the, that's why the 3-year-old doesn't go into the boxing match with someone who's much stronger, because they might both hit the right spots, but there is the magnitude, right? Direction might not be the issue. I don't know how coordinated 3-year-old would be, but definitely like 4-year-old would be fine. Yeah, they hit each other all the time. It's just the force is so weak. It's just like nothing. Get out of here. All right. The next part is thinking about reducing the force in terms of, let's say, weight. It's very easy to lift someone who's 300 pounds in a pool. Not so easy to lift someone who's 300 pounds outside of the pool. So that's one, right? One thing. But also, if you are pushing or pulling, and you do so at an angle, some of the force gets wasted in a direction that you are not actually pulling or pushing. So anytime you push an object, you try to have your arms parallel to the surface on which you're pushing. So if I am to push the chair on the floor, just because if I push this way, you see that the force is coming in at the angle. And when you decompose this motion into a vertical and forward, the vertical motion is actually the one that is wasted because it's trying to bury this chair into the floor. That's not going to happen. So all of the force that I'm exerting right now is decomposed into those two, and then whatever force, right, regarding the angle, we'll actually do the calculation now. Trig is used, obviously. Whatever force is trying to bury this object, that's wasted, and only the forward component is the one that actually pushes the chair. For pushing heavy loads, right, you usually go like this and you push hard, right? And it's not just the way you stand, it's actually that your hands are parallel. Because you can stand like this and try to push this heavy object this way or that way, you will see it's much harder. And the reason is obviously some of the force that you're trying to use is wasted. Only the parallel force is the one that does work. So if you have a crate, I can actually make this look like a crate, especially when you have time, It's a good crate. And then a person has to have a hard hat, obviously. These arms are really long, but it's okay. And big hands, all right? We can make this person fatter. It's okay. Here we go. So pushing forward, right? This is what I was telling you about. As long as this and this are parallel, all of the force goes towards pushing the object. Now, the weight of the object will still push down, which would create normal force up. And then you will have friction, which is mu k times normal force. So all of these things you learn in physics. The heavier the object, the more the contact it has with the floor, the bigger the coefficient of static friction, the more friction you will have, the harder will it be to push. If you have a situation where you have, again, well, let's now take something smaller. So you have a smaller crate, and then the person is pushing this way. That's a horrible stand. Whatever. Doesn't need a hard head, actually. The arm is coming out of the head. All right, fine. Now we see that there is an angle. And that angle there will create a triangle like this. So this is the arm length, and the force is going that way, which is decomposed into the X force, which is the one that actually does work, and the Y force, which is wasted because you can't push this object into the ground. Obviously, if you're doing this on sand, it's a different thing. But so now you see that looking at the angle theta that you have over there, you can also look at the angle of the on the top. Again, the sine and cosine here, you look at the triangle and you write the equation. You don't memorize the equation, because if I put the angle on top, then the equations, sines and cosines, swap. So in this case, fx is going to be the function f, the force F, which is, let's say you are pushing 100 pounds. So force F times the, which trig function would be there? Cosine, because it's opposite. Very good. Sorry, it's adjacent. So cosine angle theta, and in this case Fy is F sine theta. If I move the angle to be on top, they will swap. Sine and cosine will swap. Now, obviously, when you're doing the problems, you will just plug in whatever they give you, 100 pounds or 30 degrees, and you will have some numbers floating around. And they actually have a problem like that in the textbook. Since you know all the letters, you just read that stuff. Fine. All right. And actually, that's it. One more notation. Notation-wise, yeah. So just to fix this notation, we also have unit vectors I and j. So unit vectors I and j, those guys can also be used to represent the vector. And this literally means you have 2 i's and 5 j's. So graphing, you will place 2 i's in a direction of x, 5 j's in a direction of y, and technically you are adding these 7 vectors tip to toe, right, method, and you are getting your 2, 5 vector, which is the black vector in this case. It's just the alternate notation. Addition, subtraction, everything else works the way in mathematics commands. I's are added to i's, j's are added to j's, which is just x direction, y direction. And then scalar multiplication, again, you distribute over the entire thing. So everything works the same way. And that's it. That's it for the first lecture, which reviews vectors in 2D that you should know from your pre-Calculus 2 course. Now we're going to switch over to 3D, so I'll stop the stream, restart everything. We'll be back in a few minutes.